Hello and welcome. In this video, we're going to dive into two important types of first-order ordinary differential equations. By the end of this lesson, you will be able to identify, solve, and understand the methods for first-order linear differential equations and Bernoulli differential equations. We'll start with linear equations, which are a fundamental building block, and then move on to Bernoulli equations, which can be transformed into linear ones. Let's begin. First up, let's talk about first-order linear differential equations. A first-order linear ODE is any equation that can be written in the standard form, dy by dx plus p of x times y equals q of x. Here, p of x and q of x are continuous functions of x. The key features are that the dependent variable y and its derivative dy/dx appear only to the first power, and they are not multiplied together. To solve this type of equation, we use a clever technique called the integrating factor method. The goal is to make the left side of the equation the result of a product rule. We do this by multiplying the entire equation by a special function called the integrating factor, which we denote by mu of x. The formula for the integrating factor is mu of x equals e to the power of the integral of p of x dx. Let's see why this works. When we multiply our standard form equation by mu of x, we get mu of x times dy by dx plus mu of x times p of x times y equals mu of x times q of x. Now let's look closely at the left side. Remember that the derivative of e to the power of the integral of p of x dx is just e to the power of the integral of p of x dx times p of x. In other words, the derivative of mu of x is mu of x times p of x. So we can rewrite the left side as mu of x times dy by dx plus the derivative of mu of x times y. Does that look familiar? It should. This is the exact form of the product rule. The left side is the derivative of the product mu of x times y. Now, to solve for y, we just need to integrate both sides with respect to x. Integrating the left side gives us mu of x times y. Integrating the right side gives us the integral of mu of x times q of x dx plus our constant of integration, c. Finally, we can solve for y by dividing by the integrating factor. This gives us our general solution, y equals 1 over mu of x times the quantity, the integral of mu of x times q of x dx plus c. So the process is 1. Put the equation in standard form. 2. Find the integrating factor. 3. Multiply and integrate. 4. Solve for y. Let's see this in action with some examples. Let's work through our first example. We want to solve the differential equation x times dy by d, x minus 2y equals 2x cubed. Our first step is to put this equation into the standard form, dy by d, x plus p of x times y, equals q of x. To do that, we need the coefficient of dy by dx to be 1. So we'll divide the entire equation by x. This gives us dy by d, x minus 2 over x, times y equals 2x squared. Now it's in standard form. We can identify p of x and q of x. P of x is negative 2 over x, and q of x is 2x squared. Next, we find the integrating factor, mu of x. Mu of x is e to the power of the integral of p of x dx, which is e to the power of the integral of negative 2 over x dx. The integral of negative 2 over x is negative 2 times the natural log of the absolute value of x. Using logarithm properties, this is e to the power of the natural log of x to the negative 2, which simplifies to x to the negative 2, or 1 over x squared. Now we multiply our standard form equation by this integrating factor. We get 1 over x squared times dy by d x minus 2 over x cubed times y equals 2. The left side is now the derivative of the product of the integrating factor and y. So we have the derivative with respect to x of the quantity, y over x squared equals 2. To solve for y, we integrate both sides. Integrating the left side gives y over x squared. Integrating the right side gives 2x plus our constant c. Finally, we solve for y by multiplying by x squared. Our general solution is y equals 2x cubed plus c times x squared. And there you have it. We've successfully solved our first linear ODE. Let's try another example. This time, we'll solve dy by dx plus y equals e to the x. This equation is already in standard form, dy by dx plus p of x times y equals q of x. Here, p of x is 1, and q of x is e to the x. Now let's find the integrating factor. Mu of x is e to the power of the integral of 1 dx, which is simply e to the x. Next, we multiply the entire equation by our integrating factor, e to the x. This gives us e to the x times dy by dx plus e to the x times y equals e to the x times e to the x, which is e to the 2x. The left side is the derivative of the product of the integrating factor and y. So we have the derivative with respect to x of the quantity e to the x times y equals e to the 2x. Now we integrate both sides. Integrating the left side gives e to the x times y. Integrating the right side gives 1/2 e to the 2x plus our constant c. Finally, we solve for y by dividing by e to the x. Our general solution is y equals 1/2 e to the x plus c times e to the negative x. This example shows how straightforward the method can be when the equation is already in standard form. For our third linear example, let's solve dy by dx plus 2x, y equals 2x. Again, this equation is already in standard form. Here, p of x is 2x, and q of x is also 2x. Let's find the integrating factor. Mu of x is e to the power of the integral of 2x dx, which is e to the x squared. Now, we multiply the entire equation by e to the x squared. This gives us e to the x squared times dy by dx plus 2x times e to the x squared times y equals 2x times e to the x squared. The left side is the derivative of the product of the integrating factor and y. So, we have the derivative with respect to x of the quantity e to the x squared times y equals 2x times e to the x squared. Now we integrate both sides. Integrating the left side gives e to the x squared times y. For the right side, we can use a simple u substitution. Let u equal x squared, so du equals 2x dx. The integral becomes the integral of e to the u du, which is e to the u, or e to the x squared. So the right side is e to the x squared plus c. Finally, we solve for y by dividing by e to the x squared. Our general solution is y equals 1 plus c times e to the negative x squared. We've now seen 3 examples of solving first-order linear ODEs. The process is always the same. Standardize, find the integrating factor, multiply, integrate, and solve for y. Now, let's move on to our second topic, Bernoulli differential equations. A Bernoulli equation is a first-order ODE that can be written in the form dy dx plus p of x times y equals q of x times y to the power of n. Notice how similar this is to the linear form. The only difference is the y to the power of n term on the right side. If n is 0 or 1, the equation is linear and can be solved with the method we just learned. However, if n is any other number, the equation is nonlinear. But here's the good news. We can transform it into a linear equation using a clever substitution. The substitution we use is v equals y to the power of 1 minus n. Let's see how this works. If v equals y to the 1 minus n, then we can find dv slash dx using the chain rule. The derivative of v with respect to x is 1 minus n times y to the negative n times dy by dx. Now, let's go back to our original Bernoulli equation and multiply the entire thing by 1 minus n times y to the negative n. This gives us 1 minus n times y to the negative n times dy by dx plus 1 minus n times p of x times y to the 1 minus n equals 1 minus n times q of x. Now look closely. The first term is exactly dv slash dx. The second term contains y to the 1 minus n, which is v. So we can rewrite the equation as dv forwards dx plus 1 minus n times p of x times versus equals 1 minus n times q of x. And what do we have? A first-order linear differential equation in terms of v and x. We can now solve this using the integrating factor method we just learned. Once we find v, we can substitute back to find y. The process is 1. Identify n. 2. Make the substitution v equals y caret 1n. 3. Solve the resulting linear ODE for version 4. Substitute back to find y. Let's see some examples. Let's solve our first Bernoulli equation. dy by dx plus y equals x times y squared. This is in the standard Bernoulli form. dy by dx plus p of x times y equals q of x times y to the n. Here, p of x is 1, q of x is x, and n is 2. Since n is not 0 or 1, we use the substitution method. Our substitution is v equals y to the power of 1 minus n. So v equals y to the power of 1 minus 2, which is y to the negative 1, or 1 over y. Now we need to find dv slash dx. We can differentiate v equals y to the negative 1 with respect to x. Using the chain rule, dv dx equals negative y to the negative 2 times dy phi dx. Let's rearrange our original equation to make the substitution easier. We'll divide everything by y squared. This gives us y to the negative 2 times dy by dx plus y to the negative 1 equals x. Now we can substitute. Notice that y to the negative 2 times dy phi dx is negative dv slash dx. So our equation becomes negative dv slash dx plus v equals x. This is a linear ODE. In verses, let's put it in standard form by multiplying by negative 1. We get dv slash dx minus v equals negative x. Now we solve this linear equation. P of x is negative 1, so the integrating factor is e to the power of the integral of negative 1 dx, which is e to the negative x. Multiplying by e to the negative x gives e to the negative x times dv slash dx minus e to the negative x times versus equals negative x times e to the negative x. The left side is the derivative of e to the negative x times versus. Integrating both sides, we get e to the negative x times versus equals the integral of negative x times e to the negative x dx. We can solve the integral on the right using integration by parts. Let u equal negative x and v equal e to the negative x dx. Then du is negative dx and v is negative e to the negative x. The integral becomes x times e to the negative x minus the integral of e to the negative x dx, which is x times e to the negative x plus e to the negative x. So e to the negative x times versus equals x times e to the negative x plus e to the negative x plus c. Dividing by e to the negative x, we find versus. V equals x plus 1 plus c times e to the x. We're not done yet. We need to substitute back to find y. Remember, v equals 1 over y. So 1 over y equals x plus 1 plus c times e to the x. Solving for y, we get y equals 1 over the quantity x plus 1 plus c times e to the x. This was a multi-step process, but by breaking it down, we can see how the Bernoulli substitution transforms a nonlinear problem into a solvable linear one. Let's try another Bernoulli equation. We want to solve dy by dx plus y over x equals y cubed. This is in standard Bernoulli form. P of x is 1 over x, q of x is 1, and n is 3. Our substitution is v equals y to the power of 1 minus n. So v equals y to the power of 1 minus 3, which is y to the negative 2, or 1 over y squared. The derivative dv vortis dash dx is negative 2 times y to the negative 3 times dy dx. dv slash dx equals negative 2 times y to the negative 3 times dy by dx. Let's divide our original equation by y cubed. This gives us y to the negative 3 times dy by dx plus 1 over x times y to the negative 2 equals 1. Now we substitute. Notice that y to the negative 3 times dy dx is negative 1/2 dv v slash dx. So our equation becomes negative 1/2 dv slash dx plus 1 over x times versus equals 1. Let's put this linear ODE in standard form by multiplying by negative 2. We get dv slash dx minus 2 over x times versus equals negative 2. Now we solve this linear equation. P of x is negative 2 over x, so the integrating factor is e to the power of the integral of negative 2 over x dx, which is e to the negative 2 ln x, or x to the negative 2, which is 1 over x squared. Multiplying by 1 over x squared gives 1 over x squared times dv slash dx minus 2 over x cubed times versus equals negative 2 over x squared. The left side is the derivative of v over x squared. Integrating both sides, we get v over x squared equals the integral of negative 2 over x squared dx, which is 2 over x plus c. Solving for v, we get v equals 2x plus c times x squared. v equals 2x plus c times x squared. Finally, we substitute back. Remember, v equals 1 over y squared. So 1 over y squared equals 2x plus c times x squared. Solving for y, we get y equals plus or minus 1 over the square root of the quantity 2x plus c times x squared. This example shows how the power of y can change the final form of the solution, but the method remains the same. For our final Bernoulli example, let's solve dy slash dx plus y equals y to the negative 2. Here, p of x is 1, q of x is 1, and n is negative 2. Our substitution is v equals y to the power of 1 minus n. So v equals y to the power of 1 minus negative 2, which is y cubed. The derivative dv slash dx is 3y squared times dy slash dx. dv slash dx equals 3y squared times dy by dx. Let's divide our original equation by y to the negative 2, which is the same as multiplying by y squared. This gives us y squared times dy by dx plus y cubed equals 1. Now we substitute. Notice that y squared times dy slash dx is 1/3 dv slash dx. So our equation becomes 1/3 dv slash dx plus v equals 1. Let's put this linear ODE in standard form by multiplying by 3. We get dv slash dx plus 3v equals 3. Now we solve this linear equation. P of x is 3, so the integrating factor is e to the power of the integral of 3 dx, which is e to the 3x. Multiplying by e to the 3x gives e to the 3x times d v slash dx plus 3 times e to the 3x times versus equals 3 times e to the 3x. The left side is the derivative of e to the 3x times versus. Integrating both sides, we get e to the 3x times versus equals the integral of 3 times e to the 3x dx, which is e to the 3x plus c. Solving for v, we get v equals 1 plus c times e to the negative 3x. v equals 1 plus c times e to the negative 3x. Finally, we substitute back. Remember, v equals y cubed. So y cubed equals 1 plus c times e to the negative 3x. Taking the cube root of both sides, we get y equals the cube root of the quantity 1 plus c times e to the negative 3x. This example shows that the power n can be negative, and the method still works perfectly. To reinforce your understanding, here are a few practice questions. Pause the video and try to solve them on your own. First, solve the linear equation dy squared dx plus 2y equals 4. Second, solve the Bernoulli equation dy squared dx plus y equals y cubed. Alright, let's go over the solutions. For the first problem, the integrating factor is e to the 2x. Multiplying and integrating gives e to the 2x times y equals 2 times e to the 2x plus c. Solving for y, we get y equals 2 plus c times e to the negative 2x. For the second problem, this is a Bernoulli equation with n equals 3. The substitution is v equals y to the negative 2. This leads to the linear equation dv slash d x minus 2 v equals negative 2. The integrating factor is e to the negative 2x. Solving for v gives v equals 1 plus c times e to the 2x. Substituting back, we get y equals plus or minus 1 over the square root of 1 plus c times e to the 2x. How did you do? If you got them right, great job. If not, go back and review the steps. Let's quickly recap what we've learned today. We started with first-order linear differential equations, which have the form dy by dx plus p of x times y equals q of x. We learned to solve them using the integrating factor method, where the integrating factor is e to the power of the integral of p of x dx. Then we moved on to Bernoulli differential equations, which have the form dy by dx plus p of x times y equals q of x times y to the n. We saw that these nonlinear equations can be transformed into linear ones using the substitution v equals y to the power of 1 minus n. You are now equipped to identify and solve these two important types of first-order ODEs. The key is to recognize the form of the equation and apply the correct method. Thank you for watching.